Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. I'd like to start off our event today by thanking Databricks for sponsoring today's event. Databricks is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Alteryx, Tableau, Sisense, Qlik, IBM, and DataRobot, to name just a few. Now, our past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Now, today's webinar is entitled Parallelize R Code Using Apache Spark, to be presented by Databricks. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We'll have one presenter, who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon, following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation, as we'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Hossein Falaki with Databricks. Hossein is a software engineer and data scientist at Databricks working on the R experience. Previously, he was a data scientist at Apple's personal assistant Siri. Hossein holds a PhD in computer science from UCLA, where he was a member of the Center for Embedded Networked Sensing. So Hossein, thanks for being with us today. We're looking forward to your presentation. So R is the latest language added to Apache Spark, and the SparkR API is slightly different from PySpark. SparkR's evolving interface to Apache Spark offers a wide range of APIs and capabilities to data scientists and statisticians. And with the release of Spark 2.0 and subsequent releases, the R API officially supports executing user code on distributed data. Now, this is done primarily through a family of apply functions. So in today's Data Science Central webinar, Hossein will provide an overview of this new functionality in SparkR, show how to use this API with some changes to regular code with the dapply function, focus on how to correctly use this API to parallelize existing R packages, and consider performance and examine correctness when using the apply family of functions in SparkR. So Hossein, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thank you, Bill. Hello, everyone. So we're going to be talking about how to parallelize your existing R code using Apache Spark. And as Bill just introduced me, I'm a software engineer at Databricks, and I started working on Apache Spark since when it was a research project. I've been contributing to open source Apache Spark and Databricks product for past 4 years, and currently I'm focusing on our experience at Databricks. Okay, with that brief introduction, let me introduce my employer who is sponsoring this event for us. Databricks is the company started by creators of Apache Spark, who worked on it as their research project at UC Berkeley. And the company's mission is making big data simple, and that is through a unified analytics product and a platform that actually uses Apache Spark as its main engine. This is an overview of the Databricks platform. As you can see, at the core of it is Apache Spark, and we have built services on top of Apache Spark and provided infrastructure such as our proprietary cluster management framework to make the life of Spark users much, much simpler. Okay, so with that brief introduction, I'm going to start the main topic. what is SparkR for those who are new to it? It is an R package that is currently being distributed with Apache Spark, and it basically provides an R interface or front end to Spark API. It exposes Spark's data frames, which themselves were inspired by R and Pandas data frames, and offers a number of convenient functionality to move between R and Spark data frames and like operate on these objects. So basically, with SparkR, you get the benefits of Apache Spark as a general purpose engine. It's a robust distributed processing engine. You can use a variety of data sources. You can have data off heap or in distributed memory, plus all the advantages that you are familiar with when using R. It's a very dynamic environment, it's very interactive. There are tons of packages, and it offers great visualization capabilities. So let's give an overview of the SparkR architecture, and I'll be referencing this architecture throughout my talk in order to explain things and how the API is implemented. So this is a very high-level overview of a Spark cluster. We have a number of instances. One of them is going to be designated as the Spark driver, and the others are workers. In all these instances, there is a JVM instance that is running the Spark binaries. And as you know, when you read and write data using Spark, basically the workers are touching the data, and the driver's job is basically instructing the workers what to do. So all the data is being handled by the workers. This is important to keep in mind. We'll get back to it later. And as I said, you can read data from a variety of data sources. It's just examples. And there are many, many more ways of ingesting data. One of the great things about Spark is that it has abstracted the data source. So you can use Spark to interact with data no matter where it is. Now, when we add R to this picture, it starts like this. First of all, we're going to have an R process on the driver machine. And that R process is going to interact with the JVM process using a layer inside the JVM, which is called R backend. And they talk to each other over a local socket. So some takeaways from this architecture diagram is, first of all, when you're using SparkR, your code is running inside the R process. You are interacting with the R process. But your data, as you can see, is still handled by the workers. So the R process is not touching your data. Since Spark 2.0, we've added the capability of running native R code in SparkR. And in order to achieve that, we have ephemeral R processes running on the workers. There's going to be one R process per core on your worker instance. And the important thing to keep in mind is your data is still primarily handled by the JVM. It is given to the R process only when your R function has to be executed on the data. Okay, so let's give a very broad overview of SparkR API. This is how I generally categorize the API. There are a number of functions for reading and writing data, called these I/O API. Functionality for controlling where your data resists in memory hierarchy, which, like, for example, caching it, whether it's a data frame or a table. There is functionality that allows you to interact with your data frame using SQL queries, which is very convenient. There is a wide variety of the machine learning library APIs exposed in SparkR. This is under very active development, and with every release, new functionality is exposed in SparkR. So I definitely encourage you to monitor the project on this area. And also, as I said, there's a lot of data frame API. These are what you're used to with R data.frame API, and allows you to interact with your distributed data, very similar to how you would do it with local R data frames. And finally, one of the latest additions to SparkR, which is going to be the topic of our today's seminar, is the UDF functionality, and that is what we're going to focus on. There are a number of functions. We call them the apply family of functions. There are SparkR apply, DApply, GApply, and the similar functions that have the word collect in them. We'll get to more details what they are. Okay, so here's the overview. The first group, or the first UDF API is SparkR apply. At a very high level, what it does, it takes a function and executes that function in parallel over a list of elements. The next group is DApply. It applies a function to each partition of a data frame, and I will go into a lot more details about these. So just bear with me while I introduce them at a high level. And it has a second version called DApply collect. And the third is GApply, and applies a function to each group within a data frame, a Spark data frame. And it has another version called GApply collect. So let's go through each of these and introduce them in more details. SparkR apply, this is the simplest SparkR UDF pattern or function. And what it does is basically for each element of a list that you provided, and this is a local R list, not a distributed list, it will send the function that you provided as the second argument to your R workers, along with one of the values of your list, and then it'll execute that function on the worker and return the result of all of the workers as another list inside the R driver. The syntax is, as I said, pretty simple. You give it a list and a function that takes a single argument, and that argument is going to be one of the elements of your list. Okay, so what happens under the hood when I use this function? I'm going to go into some details in terms of implementation. Usually, data scientists are not very interested in this level of implementation detail, but in this case, I encourage you to keep this in mind and learn about it. And the reason is, here we are dealing with a distributed engine, and knowing how things are happening will help us greatly in terms of making sure our code is correct and our code is efficient. Okay, so I'm going to walk through the control flow of SparkR apply. As I mentioned, we have a driver and a number of workers. There's a JVM process in our driver, and on each of our workers, there's a constantly running R process on the driver and an ephemeral R process on the worker. So when the user makes an SparkR apply call, for example, the simple example I presented last slide, the first thing that happens is SparkR will grab the function that you provided along with one of the values and serialize it as an R closure. For those who don't know what a closure is, it is basically a function along with all the values and variables that are required to execute that function. Basically, with a closure, if you're given a closure, it means you have all the information you need to execute that function. Next, SparkR will transfer that binary data, which is the serialized R closure, over the local socket to the driver JVM. The driver will take that and transfer it over the network to all of the workers. So every worker will get, the JVM process will get the closure, and it will basically send it as it received it over its local socket to the R process. Now, the R process knows how to deserialize this closure. This is basically a binary file that R knows is supposed to contain a closure, so it knows how to deserialize it. After that, our process can execute it. As I said, the closure contains all the information needed for execution. Next, it will serialize the result and send it over the local socket to the worker JVM. The worker JVM will send it back over the network to the driver. The driver will send it to the R process, and finally the R process will deserialize the data. So as you can see, there are quite a few things happening when we make a simple Spark apply call. There is serialization and deserialization happening. There is some transfer over the network and execution of your code on the worker, and also there is serialization and deserialization of the result. And these are important to keep in mind because when you get an error or something goes wrong, knowing which category of error you're getting by assigning that error message to one of these general steps will help you greatly. Okay. Now let's move on to our next API, which is Dapply. Dapply is a little bit more involved than lapply because it deals with distributed data. It will run your function on every partition of your Spark data frame. So now let me explain what a partition is. A Spark data frame is a distributed collection of data along with a schema. By distributed, it means your data doesn't reside on a single machine. You are referencing your data as a single variable, but in fact, each of your workers is hosting parts of that distributed data set. And each of those parts is basically called a partition in Spark. So what does Dapply do? It will take each partition of your distributed data and send it over to the R process as a data.frame, which is a local R data frame. It will also send the R function to every worker. And we already know how that happens because we saw with Spark apply that's part of the execution. It will then execute the function on that partition of the data inside the R process. And then you'll get back your results. So let's see, there are two, as I said, there are two versions of this. The first version requires a Spark data frame, a function, and a schema. And this version will return back to you another Spark data frame. That's why you need to pass the schema. And I'll explain why. A second version takes a Spark data frame, a function, but doesn't need a schema. And this version will return the results as a local R data frame. Now, obviously, you can see if the result of your Dapply function is going to be a very large data set, you don't want to use the Dapply collect version because your result basically will not fit on a single machine. Otherwise, you can use Dapply collect. Okay, now let's see what happens on the data plane when we use Dapply. So we talked about the control plane with Spark apply. I'm not going to go into that much detail. Just basically, we'll be sending the closure over local socket to the driver, and then the driver will send it over the network to the workers, and then the worker JVM will send a closure to the R process. However, for data, the data is already on the worker JVM. So the worker JVM will basically grab its part of the data, serialize it, and send it over the local socket to the R process. And the R process will receive it and deserialize it as an R data frame. After the closure is executed on that partition of the data, the result is then serialized and sent over local socket to the worker's JVM. Now, if we have a Dapply function, we are done because we need the results as a Spark data frame, which means the partitions of it need to exist on worker JVMs. So, but if we use the apply collect, what another step needs to happen, and that is when the worker JVM gets the result, it will need to send it back over to the driver, and then the driver needs to send it to the R worker and to the R process inside the driver, and that will deserialize it as a local R process. So, although you're passing fewer arguments to the apply collect, it is actually doing more work by collecting the final result to the driver. Okay, our third API group is gapply, and it is similar to dapply in that it operates on distributed data with an additional step. It performs a grouping on your data, and then for each group within your data, it'll execute your function. And for that, it basically takes that group and sends it to the R worker and executes the closure and then returns the result. As I said before, this has two versions. The default version is gapply, where you pass it the schema and it returns a Spark data frame, and the other version is gapply collect. It doesn't require a schema and it returns an R data frame. Okay, here's how it works. Basically, that additional grouping involves a data shuffle in Spark, and Spark is very efficient at doing that and shuffling the data. So in the control plane, very similar to lapply and dapply, we send the closure over to our workers eventually. But on the data plane, after the shuffle, which is the result of our group by, each partition, which is now corresponding to one group of data, is sent over to the R process. And after the result is obtained by executing the closure on that part of our data, it is sent back. And if it's gapply collect, it is sent back over to the R process on the driver. Okay, so we have three broad categories of APIs. There are five in total. So let's see when we should use which. And the most confusing are gapply and dapply. I've seen people using one where they should have been using the other one. So here's a very simple guideline how to pick the right one. First of all, they're different in terms of signature. gapply takes a number of columns and performs grouping using those columns. Just to make it a little bit more confusing, there is another version of gapply that takes a grouped data frame. That's another type of object in SparkR, which means you already took a data frame and performed a group by on it on a number of columns, and then you take the result of that and pass it to gapply. So that's one source of confusion for people. Sometimes they see, oh, this gapply is not taking any columns. It must be behaving like dapply. In fact, the first argument in that case is the group data frame. And dapply, as we know, doesn't take a list of columns for grouping. Another difference between the two is the user function signature. The function that you pass to gapply takes two arguments. The first argument is the list of keys that are used for grouping. So for each group of data, you'll get the corresponding keys to that group. And the second argument is going to be your data as a local R data frame. But for dapply, you only get the data frame inside the user function. And finally, the main difference, the semantic difference between these two groups of APIs is data partitioning. In gapply, you're controlling the data partition using a grouping. Whereas in dapply, you have no control over how your data is partitioned. Basically, you're telling Spark, take my data as they are, however they're partitioned, and apply my function on every partition. So if your logic depends on how your data is passed to each worker, then dapply is not the right candidate for you. You want to be using dapply and strictly controlling how your data is partitioned. Okay. Now, I have learned a number of lessons throughout past year, I would say, while working with our customers who've been using Spark's UDF functionality, and also internally when we were using it ourselves. And I would like to share those, practical lessons with you, so that you don't try to come up with them the painful way. So the first thing I would like to emphasize is about how to parallelize your data. One common mistake is taking SparkR API, because it's so simple, and try forcing your logic into it. And in many cases, that involves applying it on distributed data. The one thing you want to keep in mind is that you should not use SparkR API to distribute a large data set. Let me give you an example. We had a customer who wanted to apply a function in parallel on a number of data frames, and these were local R data frames. He grabbed them and put them in a list. So he had a list of data frames, and then used SparkR API to send each data frame to a worker and run his function on it. And it didn't work because of two reasons. First, he was getting failures because Spark's control plane was complaining on transferring too much data, because control plane is not supposed to be dealing with large amounts of data. And second, when he fixed that problem, it was very slow, because again, the control plane is not efficient to handle large data. So that's the first thing you want to keep in mind. Use SparkR API only for distributing computation, not data. A related topic to that is be careful not to pack data in your closure. And what does that mean? When you are writing your user function, as I mentioned, Spark will grab that function and make it a closure, which includes all the variables that are referenced in your function. Now, if you're developing your function in RStudio or any other R environment, you can easily use any variable in your namespace, and it will be happily executing them. If you use a variable that references a large data frame, Spark will try to pack all of that data into your closure, and that will blow up the amount of data that is going to be sent over the control plane, and it will either result in failure or performance problems. So carefully inspect your user function to make sure it doesn't reference large data. If it's referencing large data, it means you can deal with it in some other way, and I'll show you how. There is a kind of a typo or a copy paste here. It should be the third bullet, instead of do not pack data in your closure, is basically trying to what I was trying to write was be careful about your partitioning. First of all, you want to make sure your data is evenly partitioned. And this applies to both dapply and gapply. If your default partitioning is very skewed, your performance will be affected, because your function will not return until the last partition is processed. If your grouping results in very skewed partitions, again, you'll have the same problem. The last broad topic I would like to highlight is how we can deal with auxiliary data. And that kind of relates to basically avoiding including large data inside your closure. This is kind of a workaround. Sometimes you need to reference a data frame, a helper data frame in your function that is passed to dapply. In that case, instead of just using it in your function, you want to make sure you carefully send that data to every worker and then use it there. And there are two broad ways of doing it. One, you can join it with your input data frame. So you have a Spark data frame as your input. You just join the two, the auxiliary data with your input data in a way that on the worker you get the right data set. A second way is pre-distribute your auxiliary data to all the workers, and on the worker, read that data again, similar to a broadcast variable. Okay. Next thing I would like to highlight on is using packages on the workers. Obviously, we are using this API because we have some complex user logic that cannot be expressed using simple SparkR API. Therefore, we're going to just grab our existing code and parallelize it. And most of the time, this involves using third-party packages. And one thing to keep in mind is that SparkR's closure capture process does not include packages on the driver. What this means is if you have imported a package on your driver, you are in SparkR environment basically, and you're using it, if you use that in your functions that are passing to dapply or gapply or lapply, the workers will complain that I don't have this package imported. So what you need to do is you need to include an import statement at the beginning of your function that is going to be executed on each worker. And what that means is that that package needs to be installed on every worker. Now, there are multiple ways of doing it depending on what environment you're using your SparkR. A lot of the cluster managers out there have features for installing binaries on Spark workers. So use whatever features your environment offers to pre-install the packages you're going to be needing in your workers. If your environment doesn't support that, I will show you can use SparkR API to install packages on workers in one step and then use it in the second step. Okay. The next thing is how can you debug your code? This is often a pain point for SparkR users, primarily because SparkR API, when something goes wrong, returns an exception. Basically, you will end up seeing a lot of Java stack traces in your R code, which is not familiar. So here are the steps I would recommend our customers go through to debug their code when something goes wrong, especially with the UDS API. The first step is to verify that your code can run, by code I mean your user function that you're passing to apply functions, can run on the driver. Make sure there's no bugs when you run it on a single machine. Next thing, when people get failures in job, I suggest they execute that code interactively in a notebook. And when they get to their failure, they'll get an exception inside the driver that will contain a sub-exception that has been thrown from the worker, and that exception will include the standard error from the R worker process. So basically, you just need to patiently open up the exception messages and find that error code from your R worker or error message. The third advice is look at the details of your job failure in Spark UI. Spark UI actually is very helpful in showing what goes on under the hood, and when something fails, it'll actually allow you to look at the failure on each worker, and that includes the standard out and standard error of the worker as well. So if the exception doesn't have any hints, you might be able to find the source of your error by looking in standard error and standard out of the worker process, which are, as I said, available in your Spark UI. Okay, so that was basically the list of my high-level lessons learned using Spark Spark Apply API. Here are a number of new features that are coming to SparkR in Spark 2.2, which was very recently released. At the time, I think when we were preparing the webinar and we were advertising, it was not GA'd yet, but now these are available for you to use. You can see the Spark ticket number. For a lot of the times, the R community, when they use SparkR, they're a little bit not familiar with how the Apache Spark or project is organized. Everything is tracked on Jira, and basically there's a ticket that you can go to and see the history of that issue, and then you'll be able to go to the pull request, or basically the patch that was submitted to the repository to address that ticket. Here's a bunch of new features that have been added to SparkR in 2.2. You can see this structured streaming API has been added. The catalog API is now completely supported in SparkR. The column functions to JSON and from JSON. If you're familiar with Spark SQL, you know what these are. I encourage you to look at the ticket for more details. Coalesce on data frames and columns is added recently. Data frame checkpointing now is supported in SparkR, and finally, multi-column approx quantile in R is supported. So these are basically, most of these are functionality that existed in Spark SQL or Spark ML library, and now they're basically exposed in 2.2. So before I jump to my demo, I want to give this highlight about how you can actually try these things. You can use our free community edition, and that's what I'm going to be using for my demo, a very, very short demo, to try out all this API on your own. And if you want to use it on larger data for more real use cases, I encourage you to check out our enterprise offering, the Databricks platform, and you can try it for, I think, 2 weeks for free if you go to databricks.com. Okay, with that, let me go to the demo part, and I'm going to share my screen. It will take, I think, 3 or 4 seconds before the screen is visible to everyone, so I'll just wait a few seconds. Okay, here's the Databricks Community Edition. And I have already logged in, and I've already created a mini cluster called SparkR. These are small clusters that we are offering for free. It only has 6 gigabytes of memory, and I'm running the latest Databricks runtime, which includes Spark 2.2. So I already have written a notebook that I'm going to be using. I've attached my notebook to my cluster, so now it's ready to execute. This is just like any R environment. I can run any R command and get the results. So the first thing I'm going to do, I'm going to import the SparkR library. We used to import this by default. We stopped doing that because we have found that people may want to import other packages that sometimes have conflicting function names. So now it's not imported by default. As the first step, I import it. Now I'm going to run this Spark Apply command. Here you see I'm giving it a list of size 2, a vector of size 2, and a function. And that function is basically calling install packages on the worker. So this is, and then I import it to make sure the installation process worked. This is something you could do if your cluster environment doesn't support installing binaries. And as you can see, I get a failure. So let's see what happens. Here, the failure message is actually very clear. You don't have to do too much to get to the actual message. And this is the message we're getting from one of the workers. It says, failed to lock directory this for modifying. So basically what it's complaining, it says that I'm trying to write into this directory, but someone else has a lock on it. And then as you can see, there's the actual Spark exception here, and that's the part that usually confuses a lot of our users. And you can see under the hood, inside it actually contains the actual message. So what is the reason behind this? Fortunately, I know it. We only have one worker, but we are calling SparkR API with two. Therefore, both of those are going to be are being executed on one inside the one container. As a result, there is this lock contention. So if I reduce that to one, it'll install this package, and we will be able to import it. And there you go. I could import it, and this is the result. Now let's use that. So I'm basically this has exposed an SVM function. So I'm just going to use it on the iris data set, which is supposed to be available on all the workers, and then get the summary of the model. And then I see another failure. So let's look at this here. You can see that it cannot find the function SVM. And this is because, as I said, the closure capture does not include library. So I need to import my library. So one might ask, how come we could install it and then use it again, but our import didn't work because we already imported it? Well, there you go. First of all, our call succeeded. But as I said, our workers are ephemeral, meaning that they're started for the execution of the function, and then they're terminated. So anything you import, and the reason for that approach is we don't want leftover state from one apply function to carry on to the next function call. We want a clean namespace for every call, and that means that if you already imported something, your next call doesn't include that import. Your next interaction with the R process. Okay, so that's using SparkR API. You saw with two simple examples. Now let's do some experiments with Dapply and gapply. So I import SparkR again. I'm going to take the iris data set and create a Spark data frame from it. If I type df here, you can see it says Spark data frame, and this is the schema. Now I'm going to use gapply. As I said, it takes a Spark data frame, a number of columns, and a function. In my function, I am simply creating a new data frame that has the key and the number of rows of my partition. Basically, this is going to return the number of entries in iris for each species. And here you can see my job is in progress. And this is the Spark UI for that job, in case you want to investigate. Here you go. We have 3 species in our data set, and there are 50 rows for each one of them. Okay, now let's use the same function for Dapply and see what we get. And here you can see I get 150. The reason is, as I said, I have no control over data partitioning. That means, however my data is partitioned, it's just going to grab those partitions and run them in my function. And in this case, my data has only a single partition because this is a small cluster and a very small data set. The solution to that, I can control my partition. So there's a function called repartition. I can use repartition with a number that will repartition randomly or with a column. And then if I use this again, I expect to get 50 rows for each partition because I already performed the group by on my data. You might ask, why is it taking so long for a small data set like this? First of all, we have a very small cluster with limited resources. But the thing to note is there's a fixed overhead involved with all those serialization and deserialization steps that and then transferred over local socket that I talked about. So if your data is not large enough, maybe you don't want to use a big hammer like Spark for that. Okay, here you can see that I got 50 rows on each partition. Now let's use the non-collect version of the API, and I'm going to be very quick here. I'm specifying a schema, and then I'm using gapply without collect and pass the schema to it. And now I expect to see 3 rows in my resulting data frame. And here we get an error. Let's look at the error. Here you can see that it's complaining about writing type, and it says I can't serialize factor. So first of all, you know this is happening in one of the serialization steps. If you dig deeper, you can actually identify which serialization step it is, but we don't need to. Basically, we see that it's trying to serialize a factor, and the problem is this data frame is returning 2 columns. It has 2 columns. The first one is a factor, and the second one is a number. But I'm asking Spark to consider the first one to be a string, and that is causing the problem. So there's a way to convert that data frame to that column to a string, and that is strings as factors. So I'm just going to pass that. And set it to false, so it doesn't convert strings to factors. And now, if I look at my results, hopefully it will succeed. You can see there are 3 parallel executions of my function. And this is the last step for. So there you go. We got our results by collecting the data frame. Okay, now, very last step. As I said, if you have auxiliary data you want to use on your workers, instead of packing it in your closure, you can send them to the workers either by joining it to your input data frame or by sending to workers out of band. Here I'm going to show you an example. I'm taking the iris dataset and writing it on file system, on our distributed file system. Now you can see that it has been written. There you go. Now I'm going to read this, because this is a distributed file system, every one of my workers has access to this. So here's what I'm going to do. Inside the worker, I'm going to read this data, and I'm going to count it. As you can see, I'm using SparkR API, and instead of passing the data directly through the closure, I'll read it directly on the worker, and this time you can see I could read it twice on 2 workers and return the numbers. Okay, so that was the demo. I'm going to go back to the slide and open it up for questions. And thank you for listening so far. Back to you,
Hossein.
Bill.
Yes, thank you, Hossein, for such an excellent presentation. So we'll get started with today's Q&A session, and I want to thank the audience for their participation. We've had a lot of questions that have come in during your presentation, and we'll do our best to get through all of them in the time remaining. And during this Q&A session, I'll leave up this screen with contact information for Hossein if you'd like to contact him following today's webinar. Now, the questions have ranged from the more or less general to some extremely specific. So let's start with a couple of the broader questions. Start with this one. How does SparkR compare to Sparkly R?
Sure, thanks. That is a great question. As I said, SparkR is an interface to Apache Spark for our users. Our friends at RStudio have implemented a different interface that is based on the dplyr package, which is very popular among our users. There are a number of differences in general design of the two packages, but at the end of the day, they're both translating our API calls to Spark calls. Specifically, if I wanted to give you very high-level design differences, SparkR tries to be very neutral. However, Sparkly R is an opinionated interface, and it is trying to follow the dplyr style of data manipulation. That's, I would say, the main difference. And we encourage both of these packages. In fact, both of them are usable on our platform. I encourage you to search for a blog post we recently published in collaboration with RStudio folks. If you search Sparkly R on Databricks, you can see examples of how to use Sparkly R on our platform. And in other platforms, you could use Sparkly R. So both of them are very good ways of interacting with Spark from R.
Well, Hossein, thank you for that answer. And similarly, we know there are other parallelizing packages like doParallel and Future. So how does your API compare to these other parallelizing packages?
Yeah, sure. So as I mentioned, both of these are basically Spark, using Spark for the distribution of closure and data, both SparkR and Sparkly R. Those other parallel implementations of R either rely on grid clusters, or they try to parallelize your code on many cores on a very large workstation. Because as I know, R is single-threaded, and you need additional functionality to run your R code on multiple threads or on to take advantage of all your cores and CPUs on a large workstation. So the other APIs basically solve that problem for either single machine or grid computes. And Spark is coming from a different perspective. We already have a general distributed computing engine which can run on a cluster of generic machines, and we already have users who know R. How can we make sure our users can use this distributed engine? You can use Spark R to run your code on multiple cores if you have a very powerful machine. And I believe that is becoming popular. But the initial intention was running parallelizing your R code on a cluster of general computing and machines, basically.
Well, thank you for that answer. Now, there was a lot of information in your presentation, lapply, gapply, dapply, and one of our audience members asked if you could please give an example of when dapply would be useful.
Yeah, so I can see they're asking because I mentioned with gapply you have control over your partitioning. So dapply is useful when your transformation or your function doesn't depend on the partitioning of your data. For example, you want to grab each row of your data and append the column to it, and it doesn't matter, and that column, it doesn't matter whether you process that row on worker 1 or worker 2. In that case, it's basically a simple transformation, and you don't care how your data is partitioned. In that case, you don't want to pay the additional cost of a shuffle, so you just use dapply. It's going to be more efficient. So in terms of you could use gapply for that, but you're paying extra cost for the shuffle, unnecessary cost.
Oh, that's interesting. Oh, thanks for that clarification. Similarly, here's a question that wants to contrast lapply and dapply, and the question is, does each worker in Spark lapply work on a partition of the original list or on the whole original list? So what are the main differences between lapply and dapply, besides the fact that they work on list and another work on data frame?
Yeah, so each worker, when you're using lapply, each worker will get a single value of your list, not a range and not the whole list. So basically, each worker will be given your function with a single value. For example, if my list is 1 to 100 and I have 100 workers, each worker will get one of those values.
Okay, all right. Thanks for that clarification. Now, here's an application question from the audience. If the function we want to apply is, for example, a min-max normalization, will the distributed execution be able to access the min-max values in the other distributions of the data frame?
Well, when you are inside the R worker, you can't use you can't access a lot outside. Basically, it's in and out. So basically, as a result, I would recommend using something like what I did with reading a file from distributed file system. Well, first of all, when you're using Spark API to do such a thing, you have to think of it as stages. So that's why MLlib, for example, for every algorithm, you can specify the number of iterations. It controls how many times you're going to iterate. And in this case, if you can do it in multiple iterations, you can't assume that every worker is going to be talking to every other worker. That is not how this API is organized. Not just SparkR, basically anything in Spark. So you can think of it, if you break it down in multiple iterations, between each iteration, you could, at the beginning of the iteration, you could read some shared data or write to it. So that is if you don't have any external system that will help you share data. Now you could do crazy things like having each worker establish a connection to a database or a memory store, and they could constantly be communicating through that memory store with each other. All those are possible, but the standard way of doing things is breaking down the algorithm to multiple iterations and going through the iterations.
Okay, well, Hossein, thank you for that clarification. I'm sorry, did you want to add something?
No, I said I hope I could capture the answer, but I can see this is a very broad question that comes from two different ways of approaching the problem, and I think it can be the topic of a lot more discussion.
I bet. This is an extremely complex and very flexible solution that you've presented to us. Well, thank you. Great answers to some very good questions. And for those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Hossein and the Databricks team so they can follow up with you after today's webinar. I have just a few quick announcements. If you'd please mark your calendars for August 22nd. That's our next DSC webinar, which is Predictive Analytics for Supply Chain Management, and that'll be presented by Alteryx. Also remember that today's taping will be available for on-demand viewing later today and can be found on the homepage of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to Databricks for their sponsorship, and our speaker today, Hossein Falaki, for his insight into today's topic. Now, my name is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on August 22nd. Have a great day.